Good morning, lads and ladies. Today is an exciting day for us because today is the first day we get to use this awesome new word, the derivative. So I'm going to show you what the derivative is today, what we use it for a little bit, kind of remind you some of our long-term goals for the class, and then we'll do some nuts and bolts calculations. Let's see, yeah, okay, so I'll talk to him now. I do want to move fast, if at all possible. I would like to let you guys go a little bit early today because I'm sure many of you know, today is the inauguration. And we're expecting this to be an exciting and eventful. So I would like it if you guys were able to see as much of that as you want. The inauguration begins at 12. So today, we begin with Katie, I am going to go ahead and mute you. I think I'm getting some background noise there. So if you do want to talk, go ahead and unmute yourself. But for now, I'm going to keep you muted because I think we're getting some background noise. Specifically, we're going to talk today about section 2.7. And then later in the week, we're going to talk about 2.8. And also, I'll let you guys know, next week is going to be your first bit of student teaching. So Haley and Tahara are going to be showing you guys next week a little bit of differentiation tricks. But before we learn the tricks, we need to learn the basics. So today is the basics. Recall that one of the two big problems, oh shit, my brain is not working, two big problems in calculus is finding tangent lines. And the idea of a tangent line, we've drawn this picture a few times, but not super recently, is that if I give you some function f of x, here's the x-axis, and some number a, can you come up to the function here and find the line that just barely kisses the graph of the function, like perfectly, like that? In other words, if the graph of the function were like a ski slope, you know, a mountain, then the tangent line would be pointing in the direction of your skis as you ski along it. So just vocabulary stuff. This thing here is called the tangent line. The point right here along the graph where the tangent line kisses the graph, that would be a comma f of a, and we call this guy the point of tangency. So today I'm going to teach you how to find tangent lines. Teach you the kind of the very, very basic fundamental tool for finding tangent lines, for solving the tangent line problem, which is a really big deal. Before I get into any of the notation and definitions, I just want to show you this Desmos graph. So here is that red graph, think of that as f of x, and this purple line right here is your tangent line. And you can see the point of tangency and the tangent line moving as I drag this slider around. So that's what tangent lines look like, right? They're the line that kind of points in the direction the graph is going. Of course, curvy graphs like this, they don't have a fixed slope. You can think of the tangent line as being the exact slope of that graph at that point. What the hell? Okay, that was all right. So you can think of the tangent line as being the instantaneous rate of change, or the exact slope of that curvy graph at that point. But since the graph is curvy, the slope changes every point. So that's what we're going to learn how to do today. We're going to learn how to calculate that thing. To find the equation of any line, like let alone the tangent line, to find the equation of any line, it suffices to know two things. What two things do I need to find the equation of any line?
The slope.
Definitely need the slope. And what else do I need? Let's see if there's something in the chat here. The y-intercept is one of the types of things we could have here, but we don't need to actually have the y-intercept or the x-intercept, just any point. Just any point on the line. If you have any point on the line and the slope of the line, then you can put these things together using the point slope formula. Which is y minus y0 equals m times x minus x0, where that point on the line is x0 comma y0. So I want to emphasize this is the reason I asked this question. The point on the line does not need to be the y-intercept or the x-intercept. Doesn't have to be either intercept, just any point on the line. And then once you have any point on the line and the slope, you can use the point slope formula to write down the equation of that line. We're going to use the point slope formula a lot in this class. And when it comes to finding tangent lines, the point is going to be the point of tangency. The slope is going to be the trickier thing to figure out. So when finding tangent lines, we will use the point of tangency for our point. But what about the slope? Well, that's trickier. It turns out the best way to get the slope of the tangent line is to think of the tangent line as a limiting case of secant lines. So in a second here, I'm going to turn the page, draw some fresh pictures. I'll give you guys just a minute to write down anything here. Everybody Gucci so far? Okay. So here's my curve f of x again. And here's my x value a. what I want to do to find that tangent line, I look just a little bit away from A. I move away from A over here to A plus H. And I form what's called a secant line by connecting the 2 points on the graph here. Okay. So I still have my point up here, A comma F of A. And the point here would be A plus H comma F of A plus H. The horizontal distance between those 2 points, the run, is just H. And here's the idea. So this thing here is called a secant line. We want to imagine sort of dragging this point over here closer and closer and closer and closer and closer to this point right here. As I do that, my secant line will slowly turn into a tangent line. We'll say this. As we drag the point A plus H, comma, F of A plus H, closer and closer to the point A, comma, F of A, this secant line gets closer and closer to the tangent line. Oh, let me see. I have another color here. Well, maybe in pencil then. Gets closer and closer to this tangent line. In your notes, you can omit the tangent line here. You have the tangent line from the last graph, so maybe it would be easier to read your notes if you just left that off entirely. But I want to illustrate for you that as I drag this point closer and closer and closer along the graph over to this point, the light blue secant line turns into the pencil tangent line, turns into the tangent line from the previous page. In particular, the slope of the secant line, which I'll write as m secant, or m sec, which is f of a plus h minus f of a all over h. I'm taking the y2 minus y1 over x2 minus x1. You can write this as a plus h minus a. So that just simplify f of a plus h minus f of a all over h. In particular, this slope of the secant line will become the slope of the tangent line as the points get closer. as the 2 points come together. So I'd like to ask you, what sort of limit do you need to take in this picture in order to bring this point closer and closer to this point? How do I bring these two guys together?
By taking h closer and closer to 0.
Yeah, exactly. I need to send h, the distance between them, to 0. That is m tan, the thing I want, the slope of the tangent line, so I'll abbreviate tangent as tan. M tan is the limit as h goes to 0 of m sec, the slope of the secant line. So he said the slope of the secant line will become the slope of the tangent line as the 2 points come together. Those 2 points coming together means you're sending the distance between them, which is h, to 0. So the slope of the tangent line is equal to the limit as h goes to 0 of the slope of the secant line. So you come up with a formula for the slope of the secant line. You send h to 0 in that will give you the slope of the tangent line. Now, we have a formula for the slope of the secant line. So this limb is this limb, but the slope of the secant line is f of a plus h minus f of a all over h. And we call this the derivative, called the derivative of f of x at x equals a, or f primed of a for short. In other words, here's your first big important calculus definition besides the limits. Def f primed of a is equal to the limit as h goes to 0, f of a plus h minus f of a, all divided by h. And this definition you definitely need to hold on to. This is the limit definition of the derivative. Some shit stuck in my teeth, sorry. All right. So if you want the slope of the tangent line, that is f primed of a. And the way you calculate f primed of a is in terms of this limit. You just crunch out this limit. To crunch out this limit, you need to know the function f, and you need to know the number a. So let's look at an example or two. Does anybody need time to write things here?
Could you like go up to like the graph?
Is this good?
Yeah, thank you.
Okay, I'll hold here for just a second. Watch out, brother. We'll survive. Okay. So let's look at an example. Let's find the equation of the tangent line to the function f of x equals 3 over x at x equals 3. Why not? This is an example from the textbook. Before I get started here, I'm going to draw the graph of this function. And you really, really, really want to practice drawing graphs by hand. Calc 1, all about graphs. Got to know the graphs. So this is the same as 3 times 1 over x. And the graph of 1 over x, that's a graph we should all know from pre-calculus, maybe even before. This thing looks like this. When x is equal to 3, f of 3 is 3 over 3 is 1. So maybe I'll call this here 3, and I'll call this here 1. This would be like 2, and that would be like 1. And this point right here on the graph of f of x when x is equal to 3 is the point 3, 1. I want to find the equation of the tangent line. I don't know what that is, but I do know kind of what it should look like. I know it should kind of look like this. So that's my goal, is to find the equation of that blue tangent line. To do that, I need 2 things. I need the point, and I need the slope. The point is easier. What is the point here that I'm going to use in my point slope formula? Yeah, it's always the point of tangency. And that's always of the form a comma f of a. So here a is 3. My point is always a comma f of a, which here is 3 comma f of 3, and f of 3 is 1. So this is the point 3 comma 1. The slope is always f primed of a, and here a is 3. So this is f primed of 3. So I'm going to need to calculate f primed of 3. And that's where I'm going to have to get into some limit work. But it's nice to set up the schematics. The point I got, it's all sorted. The picture is nice. This will be useful to check my work at the end. And the slope, I know what I need to do. I need to find f prime of 3. So how do I find f primed of 3? I use the definition. That's all I've got. So that's all I could possibly hope to use. F primed of 3 is the limit as h goes to 0. You just replace a by 3 in that definition. So this is f of 3 plus h minus f of 3 all over h. Now, what is my function f of x? Well, f of x is 3 over x. So f of 3 plus h is 3 over 3 plus h. And f of 3 is 3 over 3. And all of this is being divided by h. And I like to put these in parentheses to remind myself what's going on. 3 over 3 is 1. So this is 3 over 3 plus h. I cannot cancel anything here, right? Because 3 is not a factor of the bottom. But over here, I can cancel 3 over 3. That's just 1. And all of this is being divided by h. And now we're going to do just like we did in the homework problems from last week. We're going to grind out the algebra here until this gets to a place where the h from the bottom can be canceled. So I can send h to 0. The way I do that is by having a common denominator in the top here. The denominator here is 3 plus h. The denominator here is 1, so I multiply by 3 plus h over 3 plus h. And I get 3 over 3 plus h minus 3 plus h over 3 plus h, all divided by h. And it's important at this step that you remember all these fractions, big and little, their tops and bottoms are in parentheses. So when you do that subtraction upstairs, you remember to distribute the negative. You'll have 3 minus parentheses 3 plus h all over 3 plus h, and then all of this is divided by h. I am going to continue over here, so I'll draw a little divider. Subtracting this, I'll have 3 minus h, so I'll have lim h to 0, negative h over 3 plus h, all divided by h itself. And then I would say, okay, dividing by h is the same as multiplying by 1 over h. So this is negative h over 3 plus h times 1 over h. And we can cancel those. So I end up with lim h to 0, negative 1 over 3 plus h. And as you send h to 0 in that expression, you just get negative 1/3. So look at how I'm writing things. And in your work, please make sure you write everything I'm writing. I always write my limit. I write equal signs between things that are equal. When there's any risk of ambiguity, I write the parentheses. It's always very clear what's the top, what's the bottom. It's always very clear what we're moving in any given step. Your work should look like this. All right, as you're calculating limits and derivatives, make sure that your work is clean. We will be building throughout the semester more and more and more complicated things. So you need to get into the habit now of using clean work while they are relatively simple. This is relatively simple. So that when we get to the hard shit down the road, that is not relatively simple, you'll have good discipline and your work will be legible and you'll be able to follow what you're doing. All right, questions on the calculation here? Questions on why we started with this or how we did any of this or how we ended up here? Feeling all right? Okay, so let's contextualize this work. Why did I do this? Well, because f primed of 3, that's my slope. This is negative 1/3. This is m. So our tangent line is, we can write down the point slope formula, y minus y0 equals m times x minus x0. My point is 3, 1. So that's x0 and y0. And my slope is negative 1/3. So this is y minus 1 equals negative 1/3 times x minus 3. And that's it. That is your tangent line. Now, if you want to, you can put this into slope-intercept form. You can put this into y equals mx plus b. You don't have to. There's no real reason to, unless for some reason you're curious about the y-intercept. But if you wanted to do that, you could, and that would look like this. Y minus 1 equals negative 1/3 x plus negative 3 times negative 1/3 is positive 1. And then you add 1 to both sides. You get y equals negative 1/3 x plus 2. But the boxed answer here is perfectly acceptable. Nothing wrong with this. If you want to write it like this, you can, but you definitely don't have to. And on a test, I wouldn't waste time. You can ask ourselves, does this make sense? And if we look back at our work over here, maybe one reason you might want to calculate the y-intercept is just to check and see if your picture makes sense. And it does. Look, that's beautiful. If I extend this line, it would have a y-intercept of 2, which is what we found here. And that slope, negative 1/3, looks about right, from our picture, which we drew, remember, without any calculation. We just drew the picture based on how the graph looked. The graph we know from pre-calculus. This is it. This is how you find tangent lines. So questions on the calculation or on kind of what's going on here, like what is the tangent line? How did we find it? Anything at all. Okay. You know that old saying that Eskimos or Inuit have 100 words for snow or something? Well, mathematicians have 100 symbols for the derivative. So many different notations for the shit. Even the two guys who discovered it, Newton and Leibniz, disagreed on how you should write this shit down. So I'm going to show you some notation. And interpretations of the derivative. We've seen that f primed of a is the limit as h goes to 0 in f of a plus h minus f of a all over h. Imagine you make the substitution x equals a plus h. Then this would become f of x minus f of a over x minus a. And as h goes to 0, a plus h goes to a. So this would be the same as the limit as x goes to a. This is an alternate definition, and it's literally the same thing. To go from one to the other, you just substitute x equals a plus h. Some people prefer the second notation. I prefer the first. You'll sometimes hear this talked about as the derivative at a point versus the derivative as a function. It's literally the exact same thing. So alternate definition. If you see this, remember it's the same thing as this. And if you need to contextualize this in terms of this, remember that it's also the same thing. All right, so these are two different ways of writing the exact same thing. The trick to going back and forth is that x in the second definition is a plus h from the first definition. Notice that in f of a plus h minus f of a over h, the top, this is a rise or a change in y. Change in y values. Mathematicians have a special notation for change in, and that's delta, a capital Greek letter delta, which is just a triangle. So a change in y values we will refer to as a delta y. And the bottom is a run or a change in x values. And similarly, we'll write that sometimes as a delta x. So one interpretation of the definition, of the derivative is the limit as delta x goes to 0 in the expression delta y divided by delta x. All right, so we'll call this a bullet point. One interpretation of the derivative is lim delta x to 0, delta y over delta x. Recall that the average rate of change for f of x from x equals x1 to x equals x2 is f of x1 minus f of x2 over x1 minus x2. So if we use x1 equals a plus h and x2 equals a, this becomes f of a plus h minus f of a all over a plus h minus a, which is h. So another interpretation of f primed of a is the limit of the average rate of change as the inputs get closer and closer. Now, an average is like what happens over some time, right? Like how far did you go divided by how long did it take you? That's your average speed. But if I want to know how fast am I going right fucking at, like right at this moment, right at any one instant in time, that's different than the average. That would be called instantaneous. And the way you sort that out is as a derivative, because the limit of the average rate of change this is AKA I'm going to spell this word wrong. I'm sorry. Instantaneous rate of change. And that's a big deal. So I'm looking at an average rate of change over some interval, but then I'm shrinking that interval down to 0, shrinking the width of that interval down to 0. So I'm asking, how fast is the function changing right now? Right at this moment, how quickly is the function growing? That's an instantaneous rate of change. And this is probably the most important interpretation of the derivative. And to look a little bit deeper into this, I'm going to give an explicit example in terms of what are called position and velocity, two important concepts for physics. I'll zoom out for just a second, in case anybody needs to ask questions or make clear here any concepts. Any questions on this page? All right. So in the following example, someone has strapped me to a horizontal track. Here is the horizontal track. Here's where I'm going to start out. And they tell me, all right, dude, we want you to walk down to here. We're going to say you're starting off at some time, t0 at this position right here, which we'll call x0. And you're going to walk your happy ass down here to some position, I'll call it x1. And we'll say I arrive at the position x1 at time t1. But then they want me to turn around and walk back to here, some position we will call x2, and I arrive there at time t2. And then they want me to turn my happy ass around again and walk all the way out to here, some position which I will call x3. And I arrive there at time t3. I can talk about my average velocity. So this is an example. My average velocity over this whole trip is the distance, really displacement, divided by the time, which would be my position x3 at the end minus my position x0 at the start, divided by the time at the end minus the time at the start. This velocity can be positive, can be negative, can be 0. If I finished at the same spot where I started, if this position x3 happened to be the same as this position x0, it isn't. But if it was, then my velocity would be 0 because I would have a 0 upstairs. If my position x3 is bigger than my position x1, if I end up to the right of where I started, then this would be positive. And if my position x3 was to the left of where the position I started x0, then this would be negative. So this is your average velocity. Now I want to take this, which is all one-dimensional information, but clearly there's like some extra shit going on here. and graph it in 2 dimensions. The way we do that is we use the horizontal axis for time, and we use the vertical axis for position. So this is the time axis, and this is the x axis, where x is my position. I'll mark off some times. T0, there's my starting time. T1, T2, and T3. Notice they're not necessarily evenly spaced or anything. And then at time T0, I was at position X0. So here is the point that describes my starting position, because at this time I was at that position. And then at time T1, I had walked a little bit out, right? I walked way out here, right? So time T1, I was up here at a position I'll call this X1. And then I turned around and I walked back. So at time T2, I was at a position X2, which is between X0 and X1. And then I turned around again and I walked all the way out to the far side here, which we'll call X3. And I got there by time T3. So each one of these dots tells you my position at a given time. This graph down here encodes the same information as this picture up here. If I want to find my average velocity, that would be the slope of this pencil, connecting the points, my starting point down here with my ending point up here. The slope of the pencil is my average velocity over the whole trip. So this ratio, which is the rise, x3 minus x0, right? This distance, this vertical distance, divided by this run. That's this slope, and that would be my average speed over the whole trip. Now suppose I come in here and I decide to fill in all the little bits. Maybe I do something like this, and like this, and like this, and then I stop here. Now I've told you what I'm doing at any moment in time. From T0 to T1, here's my position changing from X0 up to X1. And then I turn around and I quickly start to walk back, and then I walk a little more slowly. If I want to know how fast am I going at any given moment, let me back up. If I want to know my average speed from time T0 to time T1, that would be the slope of this pencil. Right? My distance traveled, which is the rise, divided by the time it took me to travel that distance, which is the run. So this vertical distance divided by this horizontal distance, that would be my average speed from T0 to T1. But I'm not always going a constant speed between T0 and T1. That slope in between here changes quite a bit. So if I wanted to know my speed at a particular time A in between T0 and T1, I would need to come in here and find the slope of the tangent line at that point. This would be the instantaneous velocity. We call it x primed of A, because my function here is x, the input is t, right? So my output the thing that we normally call f, here we're calling x, the standard notation in physics, which is the derivative of x of t at t equals a. This is my instantaneous velocity at t equals a, and that has a special name. We call that v of a, v for velocity. And if I wanted to know my speed at any moment, or my velocity at any moment between t0 and t3, I would calculate that derivative. Notice that if I do this in here, call this point here B, if I come in here and I calculate this tangent line, the slope here is negative. So this guy is positive x primed of a, which is v of a, is positive x primed of b, which we would also call v of b, this is negative. And you want to know how to interpret this in the context of the motion problem here. The fact that my velocity is positive here, the fact that this tangent line has a positive slope, means I'm moving in the positive direction. Moving in the increasing x direction. And the fact that my tangent line here has negative slope, or that my velocity is negative, means I'm moving in the negative or decreasing x direction. And these turning points on the graph, these are places where I turn around. Those correspond to me changing direction. Okay. So we have about 5 more minutes before I was hoping to wrap up class. I did want to wrap up a little early today, so you guys can watch the inauguration if you want to. I'd like to take a look at just one more quick example here. Before I do that, are there any questions on this particular problem? Okay. So suppose I tell you I've got a particle in one-dimensional motion. Right, like moving along a track, like I was in that last guy. Whose position in meters at time t, measured in seconds, is, fuck it, we're just going to go x of t equals 1/2 t squared. I'd like to find the instantaneous velocity when t is equal to 4 seconds. Well, the instantaneous velocity is the rate of change, the instantaneous rate of change of position. So I need to find the instantaneous rate of change for this position function. What I'm after is x primed of 4. That is v of 4. And this, by definition, is the limit as h goes to 0 of x of 4 plus h minus x of 4, all divided by h. So I'll continue the calculation down here. This is the limit as h goes to 0. I just have to plug in from my function now. Since x of t is 1/2 t squared, x of 4 plus h is 1/2 times 4 plus h squared. X of 4 is just 1/2 times 4 squared. And downstairs I have this h. You can factor out the 1/2, and I think that's worth doing. So we'll have 1/2 times 4 plus h squared minus 4 squared all over h. And now we can start working with the algebra. 4 plus h squared is 16 plus 8h plus h squared minus 4 squared is minus 16. The 16s eat each other up. I get limit h to 0, 1/2 times 8h plus h squared all over h. And then you can factor out an h. This is lim h to 0, 1/2 times 8 plus h times h like that, all over h. And we can cancel the h's. The bottom will become a 1. So I'm left with lim h to 0, 1/2 8 plus h all over 1. And now, since there is no more h downstairs, I can send h to 0, and I just get 1/2 times 8 plus 0. You can write the over 1 if you want to. You don't have to anymore. That's 1/2 times 8, that's 4. And this would be in meters per second, because the distance was being measured in meters and time was being measured in seconds. All right, so this is where I'm going to leave you guys for today. Next time, we're going to talk about how to understand the derivative as a function. We're going to learn how to do these calculations more generally, like where you have a variable here, right here, instead of the number 4. We'll figure out how to do this for all times t. And then that is going to lead us to studying the derivative as a function in its own right. Once we have that, we will practice some more with calculations. And then you guys are going to be ready to start learning differentiation rules, which is where Haley and Tahara are going to help us next week. So next week, Haley and Tahara are going to show us our first few differentiation tricks. But for this week's homework, even if you know some differentiation tricks from the past, you need to be using these limit definitions for your calculation. I'll tell you now, there will be problems on exam 1 where I require you to use these limit definitions in the calculation. If you use some tricks that you knew from high school to calculate the derivative, instead of following those instructions, I won't be able to give you credit. So please take this week's homework earnestly, even if it's material that you've seen at some point in your life in the past, and try to learn it a little more deeply. If you run into any problems, you have any questions, don't hesitate to ask for help. I do have an office hour today from 1 to 2 p.m. And you're welcome to drop by that, but I'm going to go ahead and let you guys go now so you can tune into the inauguration if you'd like to watch it. That is all I have for you today. Tahara, if you could please send me an email or a Canvas message just as soon as you possibly can, so we can talk a little bit about next week. I had a chance to meet with Haley the other day, but I don't think you and I have had a chance to really talk. So if you could do that, I would appreciate it. Yeah, Thomas,
All right.
we're also going to have a meeting here to discuss your materials and make sure everything is prepped. Thomas is going to be doing the product and quotient rule, which will be a little later next week. So Thomas, if you can come by my office hour, that would be great. We can talk through your materials then. And Tahara, if you could send me a message or drop by the office hour today, either one of those would be good. All right, I'm gonna let you guys go. Have a good rest of your afternoon. Take a look at that inauguration if you have a chance to. And otherwise, I will see you all on Friday. There is a new homework that's gonna open today. It'll be open in just a few minutes. All right, take care.